This is part 5 of lecture 11 of ELEC5300. We're going to start our discussion of principal component analysis just by motivating the problem. So principal component analysis is actually the same as the Karhunen-Loew transformation and vector orthogonalization that we just studied in the last section, but it's kind of formulated in a way that even though it results in this idea of data whitening, it's formulated in a way that kind of makes no mention of data whitening. And so the way it's formulated is as follows. It says we have, let's say, a set of data in a two-dimensional space, right? So each one of these red points is a data point, right? And they're described by two numbers, x1 and x2. And so then we can say, well, what I'd like to be able to do is describe where these points are, but I only want to use one number, right? And so how am I going to describe these things, which depend on two numbers, by only one number? Well, the way I'm going to do that is I'm going to define a subspace, right? The subspace is a one-dimensional subspace, or a line, sitting in this two-dimensional plane that's shown by this purple line here. So that's a subspace. It turns out it's the principal subspace, but just for now, let's just say it's any old subspace. And so what I can do is I can say, well, if I know this subspace here, if I set this subspace, then I can describe each of these points here, the red points here, by a distance along this subspace. Right? Well, what distance along the subspace? The distance is the distance to the green point here, which is closest to the corresponding red point here. Right? So this red point here maps to a green point here, where the green point is the point on the line that is closest to the red point. And so we know that if we connect these two together, if this line is as short as possible, the blue line is as short as possible, then this angle here should be 90 degrees, as should all the other angles here as well be 90 degrees. And so now I can say, well, okay, now what I've done is I've taken all of these points and I've projected them down onto the line, and now I can just talk about, well, where these green points lie along the line. Now, when we're choosing this subspace, then you can say, well, you know, why did you choose this this purple subspace? Why didn't you choose some other subspace? For example, let's draw another possible subspace. Why didn't you choose, let's say, this subspace here? Well, if I chose that subspace, what I would do is this point would project onto here, this point would project onto here, this point would project onto here, and this point would project onto here. Right? I say, well, I also get a variation for the different projected points. So why is this purple line better than this line that I've drawn here? And one thing you can say, well, it looks like here that, you know, all the points are kind of like relatively close together, right? So I haven't really separated out the points, even though these points are widely separated. This kind of like, I'm kind of hiding that separation, right? Whereas it seems like on this purple line here, the green points are more spread out than these points along this line are here. And so one way you can say is, well, I want to choose the subspace, which will be the best subspace, or now we'll call it the principal subspace, such that the variation or the variance of the projected data is as large as possible, the spread. There's another way you can look at this, and it turns out it will give you exactly the same answer, and that is to say, well, when you actually project onto the subspace and you say, well, I'm going to describe this point by the green point here, then you actually introduce an error, and the error is given by the length of this blue line. Right? And some data points are going to have a larger error than other ones, but what you might do is say, well, I'm going to average all those errors together. Right? So that's what I'm going to call the average projection cost, the mean squared distance between the data points and their projection, and that's really the average squared length of these blue lines. And what you want to say is, well, I want to lose as little information as possible, so I want these green points to be as close as possible to these red points, right? And I have to move this around, and for different purple lines here, I might, stretch this one, but make this one smaller, and so I kind of have to find a trade-off between all these different errors, and then finally come up with one subspace here. But if I look at this subspace and I compare it with this subspace here, it seems, well, definitely these blue lines here seem to be smaller on average than these longer red lines here. So this one also, this purple line, does seem to be better than this other possible direction over here. So this has many different applications. One of the key ones that people have talked about is this idea of dimensionality reduction. So typically when we have, let's say, a problem to do with in image processing, for example, maybe a classification problem, I want to, for example, maybe recognize these numbers 3 from the image. My input is typically a very, very large, high-dimensional image. So, for example, if this was a 100 by 100 dimensional image, the data dimensionality of this one might be 10,000. This one is actually probably not 100 by 100, but probably something more like 30 by 30, but anyways, 30 by 30 would still give you about 900. However, I look at the data, it says, well, I don't really seem to need 900 numbers to describe what I've got here, right? Because they're all the same image, right? It's just the same image of a 3. The only difference is I've moved it up, let's say, or moved it down, or rotated it a little bit to the left or a lot to the left. And so really all I have to say is, well, I have a 3, and to specify which one of these images is, I can just tell you, well, where's the center of the 3, the XY location, and how much did I rotate it by theta, right? So even though my data is a 10,000 dimensional image, actually there's only kind of 3 degrees of freedom. And so what we say is that the data points live on a 3D subspace or a manifold of the data space. And so that just suggests then that even though my data has this many dimensions, I don't really need that many dimensions to describe it. And so then the question is, well, how can I figure that out just by looking at the data? Right? Just by looking at this, how can I figure that out automatically? And so principal component analysis is a way to do that. Now, for this particular problem here, actually PCA wouldn't be effective because the mapping from these 3 numbers to the data is actually nonlinear. And so PCA assumes that the mapping is linear. But still, PCA is quite commonly used in image processing. For example, for describing faces is probably the most well-known example of use of PCA in images. So let's finish up by just talking about the general formulation. So the idea is that we have a large number of measurements from which we want to discover this subspace. Each of the measurements is an xn. It's a column vector where the column length is d. And I have n of these, right? So I can put them all into this big data matrix, which looks like this. And so typically I'm going to have a lot of measurements, so this is going to be much longer than it is tall. But still, the data dimension here is not small, right? So for example, it would be 10,000 in the previous example. And so what I'd like to be able to do is actually say, well, I don't really need all d numbers to describe this. I only need m numbers where m is less than d. And so what are those m numbers, right? Well, I can say, well, each data point, xn, I'm going to say can be approximated by this x tilde of n, where the x tilde of n is just equal to some mean vector, which is kind of the average location of all of these guys. So that kind of allows me to only estimate the difference between the average value, right, and the particular value here. And then I'm going to take m numbers here, alpha sub ni, so n describes which data point I have, so really I here runs from 1 to m. And there's m of these alphas for each data point xn. And I'm just going to use these numbers to weight different directions in the subspace. Sorry, different directions in the data space. Right? So each one of these is a direction in the data space. Since the data space is d-dimensional, these are d-dimensional vectors just pointing in a certain direction. So since I'm only interested in the direction, I'm going to assume that they all have unit length. And the alpha then just tells me how far I go in each direction. And what I'm going to do is generally to completely specify every point I'll need d directions. And so instead of that, I'm just going to try to choose m directions to describe the data point. And I want to choose these m directions as well as possible. So that's the general formulation, and we'll tell you how to solve that with these two interpretations. The first one being trying to find the direction here, u1, which is going to maximize the variance of the green dots, right? And alternatively, we can also try to find this direction u1 that minimizes the length of all these blue error bars. So we'll do that next time for the maximum variance case.